Hello and welcome to the flipped instructional session for Physical Science Semester A. We're still looking in Unit 1 at Lesson 1.04, Physical Systems and Models. So as we get started, be sure to take notes during the recording. We want to get the keywords and important content off of each page, and make sure you title your note page with the lesson number and title. So beginning on the science homepage, we'll go into content and scroll down on the side here to 1.04, physical systems and models. So there's only two parts that we'll be checking off here. And the introduction gives us some background information. So we're talking about models. Here's your first definition. Models are used to predict behaviors in the real world. So an example, we're looking at this picture of a rocket. Rockets accelerate to supersonic speeds as they fly through the atmosphere. Engineers must know how the rocket behaves at those speeds so that it maintains a stable flight. This model rocket is placed in a wind tunnel that uses large fans to move air at supersonic speeds. The model is coated with pressure-sensitive paint. During the test, the model is illuminated with blue light. Areas of the model that experience high pressure will brighten, while those that experience low pressure will dim. So a couple questions to think about. How is the model similar to the full-scale rocket? So if we look at it closely, the design is probably the same. The dimensions for the things on the side here are probably in proportion to the larger part. So there's probably a lot of similarities. The scale basically matches the rocket's shape. So why is it a good idea to use a model before building an actual rocket? So there's probably a lot of things that you can think of. One, it's cheaper to go through and test on a model before spending the money, right, to actually build the full thing. But it's not practical to launch fully assembled rockets and observe what happens. So we definitely want to use a model first to troubleshoot. How could engineers use the model to predict how a full-scale rocket will work? So they're basically able to simulate what the rocket will experience in space, and based on what they're able to simulate, they can make adjustments. And so they can film the test in the wind tunnel and allow engineers to analyze that data to predict how the real rocket will perform in flight. Okay, so our lesson goals here will be 1, distinguish between a closed system and an open system. 2, to describe and explain a model system physicists have used to represent a real phenomenon. So 3, we will describe how scientists use models to represent and predict real phenomena in the physical world. And 4, we want to explain that models change to accommodate new discoveries and observations. So these are important things that we'll definitely want to make sure we have answered in our notes. All right, so as we move forward and look at how do you study part of the universe, so we're talking about physical systems and models. We know that scientists and engineers use models, and we are talking now about how they apply that into studying the universe. So the universe is big and complex, and everything in the universe is interconnected. It's difficult to study how something behaves when it is interacting with so many other things. So to study a phenomenon, we make generalizations and model part of a physical system. A physical system is a group of things that interact with one another. So that's a definition that you want to have in your notes, the physical system. And then understand that a system can be as small as 2 atoms colliding, as large as the entire universe, or as complex as the Earth and all that it contains. A complex system, such as the Earth, contains many interacting systems within it. Another thing you can think about here is the human body. We know that there are many complex systems in our bodies: our circulatory system, our respiratory system, skeletal system, and those interact with the systems to complete our body as a whole. So if you want to study how meteors fall from the sky rather than study meteors directly, you could create a model that's a smaller system and then compare your model to the real phenomena. Okay, so as we start looking down here, we're getting into now physical systems and defining if they are open or closed. So you'll want the definitions written down, and I always find it helpful here as well to list some examples. So some physical systems can interact with their environment by exchanging matter and energy. Such systems are called open physical systems. Okay, so open system is something that can interact with and exchange matter and energy. That means things can come in and out of that system. So an open physical system can be affected by the outside environment by an exchange of matter or energy. A closed physical system is isolated from its environment. A truly closed system doesn't exist. But for all practical purposes, a closed system does not exchange matter and energy. So for an example, an insulated drink container, like a thermos, is a closed system. Once the lid is on, the thermos keeps the drink warm or cool because it does not exchange heat or matter with the environment outside of the container. So think about that, write the definition down of a closed system, and the thermos example is a really great example. Eventually, the drink in the thermos will reach room temperature, but the process is very slow, and we can think of the thermos as a closed system. Physical models replicate and simplify systems. So physical models can be made by replicating and simplifying systems. This in green, I would definitely have in your notes as well. And a scientist studying how objects fall through air or water may use models to observe how fluid forces affect a falling object. So this photograph shows an example of a physical model used to study how objects fall. In the model, a shape covered in red dye is dropped into a tube of liquid soap. The object falls very slowly through the soap, and the disruption to the fluid can be observed by the path of the red dye. You might use a model like this to learn more about fluids or to improve the design of a vehicle that travels through water. So models can be simple. Atoms and molecules are too small to see, but scientists use simplified drawings or sketches of atoms to better understand their properties and behaviors. So you guys have seen something like this before, and that is a very simple model. Models can change. Our understanding of the universe changes as we continue to experiment and gather information. As we learn, models are adapted to fit our new understanding. We don't know that matter was made of atoms for thousands of years. We didn't know that. So the original model of an atom was quite simple, and now we know that it is more complex. So we started out with thinking this was our basic model, and then we learned a little bit more and went to this model, and then we learned a little bit more about electrons and outer shells. We went to this model, and then finally we've set on this model as we learned even more. So models can change. So the things that you want to have out of this on types of models, I would have everything in green. So models replicate and simplify systems. Models can be simple, and models can change. So those would be great things to have in your notes. Computer simulation models complex. Computer simulations model complex situations. Computer simulations are mathematical models, and that they use some simple rules to simulate more complex phenomena. So for example, this simulation follows simple rules of mechanics. It will simulate horizontal and vertical motion of an object. It doesn't use special equations for the purpose of displaying how objects move through the air. It applies basic horizontal and vertical rules of motion to an object, and more complex behaviors emerge. So try it. We're going to drop the balls, bounce the balls, and roll the balls down the ramps. All the objects are mathematical simulations, but observe how they bounce, roll, and fall like real balls. All right, so we're able to pick them up and see how they behave. So just because of the programming and how the rules of mathematical equations that were put in, we're able to understand how these different balls will react when they're placed on different surfaces and heights. So models do have limitations. That's something you want to write down too. They help us understand the universe and make predictions, and they're also used to simulate reality, but all models have limitations. Engineers use models to test designs. Engineers try to solve problems through design and will use models to test their ideas. These models may be mathematical simulations or smaller physical models designed at a smaller scale with less expensive materials. This picture shows an engineer examining designs for a support structure. Rather than create a full-scale solution, she is making small models with a 3D printer. Model systems are important in physical science. The universe is too big and complex for physical scientists to study. Instead, they choose a piece of the universe, a physical system, that can represent the universe as a whole in some aspect. Then they choose a simple analogy or model of the physical system to isolate relevant variables, formulate a hypothesis, perform an experiment, and test the hypotheses and theories. Each model system has assumptions and limitations. The results of experiments in the model system will verify or refute hypotheses and theories. Valid hypotheses and theories should describe and explain the behavior of physical systems and the universe. All right, and we're on our last page here. So we're going to look again at one more model, the behavior of the balls in the system. And we did this in an earlier lesson. If you remember, we bounced all of these. We were kind of able to see what they did when they went at the same time. And so what does the simulation model? Basically, the simulation is the picture you're seeing, the movement and everything. So we are looking at the behavior of various types of balls when they're dropped from a certain height. Some of the limitations here are that the simulation cannot show the change in the shape of the balls as they bounce. So remember in that lesson when we talked about elasticity and the ball compresses a little bit. So it doesn't show that. And then it also doesn't show damage to the balls over time. So eventually these things get worn out, right? You've seen a worn out tennis ball before. So the model is not going to reflect the difference in the way a ball would bounce when it's new versus not new. And then why are models useful? They provide a way to analyze and understand systems. So this last part here I would put in your notes as well. Okay, models are useful because you can analyze and understand systems. All right, so as we finish up this lesson, we have completed the 2 things that we needed to do, and we're heading back, so you will be ready for your next lesson. And just a reminder, check for your flip follow-up. You can come to 1 science session a week unless there is something additional scheduled that might be helpful. Attend a help lab on Monday if you needed any extra support or have questions, and always have fun. Have a great day.